Assalamu alaikum, hello everyone. My name is Abdul. I'm from Kochi University. Today I present the paper titled on Blockchain Assisted Energy Sharing Algorithms with Heuristic Data Across Microgrids. We are all tired, I'm tired, I think also we are all tired, but I hope that this presentation will be a bit different than the other ones that we have seen from the topic point of view. So we'll have a brief introduction, we'll talk about our main contributions also briefly, then we'll talk about what is energy sharing and versus energy trading. Then we'll talk about the experiments that we have done, and finally the results and conclusion. So, as a brief introduction, the our need to energy is increasing with time, and that's like kind of linearly or maybe exponentially. But we need energy more and more nowadays. For that reason, it's getting, let's say, more expensive, etc. So some people started to install their own energy sources at their homes, for example, solar panels. And most of those home installed energies are, let's say, kind of renewable energy. We can see, for example, it's expected in 2023 to be about 17 million homes in the US itself having its own energy. So from that point of view, we have some new, let's say, terms have appeared. Consumers is the ones that we know, which are people who need energy. They buy energy all the time. And prosumers, they are those people or those houses who have they need energy, but at the same time they generate energy. And finally, we have what's called microgrids. Microgrids is the, let's say, collection of multiple consumers, prosumers, distributed energy resources, and those microgrids can work by themselves as isolated mode or with the utility grid. So this is a brief introduction. Now, all of us, we know what is called the trading. Trading is you like to get something, but for money. So you pay money and you get energy. For example, if a consumer would like energy from prosumer, he might get it by paying him some money. And generally, like prosumers offer energy at lower prices than the utility grid. However, if for some reason that consumer doesn't have money, let's say for because he is poor or maybe because that of some disasters that happen, we cannot do any trading. That's why we have what's called energy sharing. And in energy sharing, we are going to transact energy, but some for some non-monetary benefits or maybe some indirect monetary benefits. So just to make it clear again, because energy trading and sharing is used a lot in the share exchangeably, but in real they are not the same. Trading, we pay money. Sharing, we don't pay money directly. We have to find another ways to facilitate the transaction. So our contributions in this paper, we have previously introduced the energy sharing using batteries in another paper, but we tested on a data set that we generated for individual houses. Now we have found another data set that represents, let's say, microgrids. So we wanted to verify that is our results previously good or not? Are we consistent? Also, we proposed a new or a third novel battery-based sharing algorithm. We call it sharing. And finally, we demonstrated, like within this paper more, that installing batteries at consumers or prosumers is advantageous. So again, just remember, let's keep energy sharing normal, no direct payment. I'll send you something, you will not pay me anything. We'll have to arrange something else. What we have proposed is we are going to use batteries. So in general insistent, especially with increasing usage of energy sources themselves at homes, people will be having batteries or energy storages at their homes. So what we proposed is instead of getting money directly, for me as a consumer, I'm going to send you the energy and you will store it on your battery at your house so I can benefit from it in the future. And in return, I'm going to send you some energy to be used for yourself. So this is what we called, or how the main concept about battery-based sharing. The first algorithm that we proposed before, it was called centralized energy sharing. We call it centralized because we have a third party here. This third party is facilitating the sharing process. So this third party, in our case, it was a smart contract, will pay that consumer money directly, and the consumer will get energy. Again, this energy, part of it will be used for his own needs. The other part will be stored on the battery. For what purposes? For the purposes that this smart contract or this third entity will try to sell this energy that was stored on the battery in the future. So we can see like between the prosumer and the consumer, there is no direct money payment. That's why we call it share. The other one that we have proposed previously also is peer-to-peer energy sharing. So we don't have a third party now. Now the consumer himself is going to share the energy as before. Part of it will be used directly for the consumer's need. The other part will be stored on the battery. And that consumer himself will try to sell this stored energy on the battery in the next, let's say, defined time steps. So again, here the peer-to-peer is trying to sell the energy. What we propose later is what's called selfish sharing. In the selfish sharing, I'm not going to try to trade it in the future. No, I'm going to try to use it for my own need. So I'm going to share energy with others only if I predict or if I know that in the future I might need it. That's why it's kind of selfish. So I don't share it for other purposes. So again, to compare the three algorithms, centralized, I have a central entity facilitating the sharing, paying the consumer, try to sell this energy. The other one, the peer-to-peer, the peer himself is trying to sell this stored energy in the battery. And here, the main difference between the selfish and the peer-to-peer is the peer himself is going to use it for his own purposes. He's going to get this energy back and use it for his own needs. This is decentralized sharing. I'm not going to talk about it since it's from a previous paper, but in the system generally, it's not very logical to have only sharing. So what we'd like to do, for example, as a prosumer, you would like to sell energy first to get profit. So that's like the nature of people. After you get the profit, if you have extra energy, you are going to share it. So that's what we had before in the centralized sharing. I have trading first, then sharing. The same we have it's also in the peer-to-peer, we have a trading phase, then we have the sharing phase. However, in the selfish sharing, we have sharing first because again, I'm selfish, let's say prosumer, I would like to get share energy so I can use it in the future for my own needs, and then I'm going to trade. So those are a bit technical details about the algorithm. We have what's called beta. This is the fraction of energy that's going to be used by the prosumer himself to get his own needs of the energy. The other fraction, which is 1 minus eta, will be stored in the batteries of the consumer. Tau is the time step, so I'm not going to store the energy that on that consumer's battery forever. There's that kind of deadline for that or time step. PT is the pricing. We have a fixed, say, pricing at each time step according to the equation we have in the paper. And again, as we have said before, this is kind of selfish behavior by that consumer. We have the selfish sharing first, and then we do the trading. So that's like emphasizing his own selfish behavior. So if we'd like to talk about blockchain, this is called blockchain conference, it is like application of the blockchain. So we are using the blockchain itself as a platform to make our system decentralized, a single point of failure, and to make it resilient and transparent. If we go and dig into the blockchain itself, what do we have exactly on the blockchain? We can see that we have the trading process itself is on the blockchain, the sharing process itself is on the blockchain also, and receiving the request for either selling the energy or I would like to buy energy or I would like energy to be shared with me, all of that is being held by the blockchain. For the experiments, for the blockchain itself, we have developed the smart contracts using Solidity. We did some few tests on it, but for the experiments, we have data for about 3 years, hourly data. So it's not feasible to send by simulation to the blockchain, send request via Web3 and then get wait for the result and get it back. It will be very time consuming. We did simulations only on Python. Again, with the pricing, I've hidden this slide to save time. So this is the pricing question I've talked to you about. We have the pricing generally between the feed-in tariff, which is the money that you are going to get from the utility grid if you'd like to sell the energy to the utility grid. And the upper limit of this pricing equation is the getting energy from utility grid. So this pricing equation will try to make both the consumers and prosumers happy because I'm going to sell to consumers energy at lower than the rate that they are going to pay to the utility grid. I'm going to pay prosumers at a rate that is higher than what the utility grid would offer. This is the utility grid price that we get energy from. This like represents the demand response ratio. And finally, like the price at current time step is kind of related in somehow to the previous time. For the dataset, again, in this paper, we have used more realistic datasets compared to our previous one. We used a dataset that represents kind of microgrids. We have 16 counties in Estonia. Within or the whole number of clients or microgrids is 69 microgrids. So some of those are businesses, some are non-business clients. Again, the data is from Estonia. This is the client's count per county. And finally, this is the how much energy is produced by each prosumer or each microgrid itself. We have two different scenarios in our simulations. In one of them, we assume energy can be traded and shared only within the county itself. So I cannot transact energy to other counties. The other scenario is we have between microgrids energy sharing and trading. So it doesn't matter in which county I am, I can transfer energy to other counties. If we talk about the results, those are too many things. I would like to focus only on the most important parts. If we take a look at the energy that we are drawing from the utility grid, the ones that we buy from the combines, we can notice that it's being reduced. Like when we use, this is normal trading, no shrink at all. This is trading, but we have enabled battery. That's why we said like the usage of battery is important in general, disregardless of the sharing itself. But when we enable sharing, we can notice that all the free sharing algorithms have reduced the amount that we get from the utility grid. And most of the time, this energy that we get from utility grid is sourced from non-renewable resources, let's say using carbon or using oil. So kind of we can say that this sharing algorithms also reducing the footprint, the carbon footprint. If we take a look at the energy that was shared, so again, shared, it means that there was no direct payment by those consumers. The consumers didn't offer payment, they offered only their batteries as a utility to be used. And if they are poor people, we can say like we have shared this amount of energy with pure people, with poor people. If it is, let's say, in disaster scale, again, we are offering this amount of energy in what? So it is about 100 megawatts offered in different scenarios. We can see also within microgrid, we have the peer-to-peer sharing is giving the most amount of shared energy. Finally, if we take a look at the results from a monetary point of view, from financial point of view, this is the total paid minus earned. It represents the total, let's say, expenses that has been in the system. The lower, the better. And we can see that trading with battery in this within county was giving us the best results. If we take a look at the results from the across county scenario, again, we can see the enabling batteries, even only with sharing, with trading itself, is very beneficial. So again, we are emphasizing this point. And if we take a look again at all of the sharing algorithms, all of them are reducing the amount that we are drawing from the utility grid. Again, the amount of energy that was shared, that was not that consumers got without paying any money, we can see that peer-to-peer also is achieving the higher value. Finally, if we take a look at the, again, financial point of view, we can see that the peer-to-peer, in this case, between microgrids scenario, was the best in reducing the costs for the whole community, as a community, not for individuals. As a conclusion, we can say that we have seen how batteries are beneficial in reducing dependency on the utility grid itself, and thus reducing the carbon footprint. We can see that as percentages between 5 point something and 6.12, like reducing the amount again that we get from the utility grid in the sharing algorithms in different ones. In the between microgrid sharing, we notice that the peer-to-peer sharing is the best in reducing the cost, while and also the utility grid dependency. However, in the within microgrid sharing, where I can share and trade only in one microgrid, we can say that the trading with battery only, no sharing at all, was the best financially. However, the peer-to-peer sharing was the best from reducing the grid dependency. For future work, we'd like to analyze those algorithms, complexity analysis. We'd like to study the gas cost also because we did simulation in Python only. And we'd like to use AI to increase the profits of those sharing algorithms. And finally, use AI to predict the needed energy that will be used in the selfish sharing. Because in our scenarios, we assume that those prosumers already know what they are going to need in the future. That's it. Thanks for attending. I have 10 seconds.
Certainly, very much. Thank you. many questions, and I don't spend all time. A group of my colleagues in my university decides this very important task,
Oh,
and I give you some contract